To start this video, be sure to watch the previous video first, the one with power function, power model, to know the significance and the importance of transformation of models. Now, this model is not a power model, but it's called an exponential model because the variable x is on the index, as opposed to power model, the variable is the base. Now, part A, express ln y as the linear function of x. So before we had y equals to mx plus c from core maths. Now the y would become ln y. So we want something ln y equals to mx plus c. So we start out with the original function. And because we want ln y at the end, so we apply ln on both sides. And so ln and e cancels out and kx goes down. So I move this to the front and this constant will be here. And so part B, we want to estimate the values of m and k here. And because the new y variable is ln of y, then I would take these y and apply ln to all of them to get these numbers. And the independent variable is x. And so we don't do anything with them and we line up here. And so if I let capital Y to be the new dependent variable ln y, then this whole thing would become capital Y equals to kx plus ln m. Then I plot these 5 points onto the graph and I connect them by using a straight line as accurate as possible. Now we're going to use the line or some of the points to approximate this slope here. Individually, each of these 5 points, okay, 4 of these are actually pretty good fit to the line, except this one, so we don't use this to calculate slope. Now, if 4 of these are good, then maybe we pick the head and tail. In other words, we pick this point and this point to calculate slope. And so using the slope formula, we get negative 0.2 for k. And now we try to find m by looking at this big y-intercept, which is this point. So when Lm equals to 1.1, and so m equals to e to the power of 1.1, and so it equals to 3. So now finally, we are doing some approximations or prediction. When y equals to 0.6, find the x. So from part B, we've got these two numbers. So y equals to 3e to the power of negative 0.2x. So then we substitute 0.6 in place of y. And then we apply ln on both sides. And so the prediction would be 8. So here's an actual application of this kind of modeling. So a researcher finds that the amount of sales in $1 million of a newly launched camera after T weeks, that's the time from the start of promotion, can be modeled by this formula here. And of course, T must be greater than 0 because it's time. Capital A and K are some constants. So part A, we want to express this thing as a linear function of T. So we start out with the original function here. And because we want s and square root of t to be together like that, so we move this part to here first. Now, because we see an ln here, we apply ln on both sides. And so when these two cancels out, this comes down, and this would be our answer for part A. So part B, let's say we've done the plotting of the graph, and we've calculated the slope and picked up a point. We found that the slope is 0.04, and the graph passes through, that means the line passes through this point. And we want to find A and K right here. So how should we do this? Now for this one, because this is a constant and this is the independent variable, and so this part, this constant 2 times k would be the slope. And so 2k equals to 0.04 and k equals to 0.02, easy. Then we use this point and substitute into this equation for us to find k. So I sub this independent variable into the t here, that is right here. And this is the big Y right here, the whole thing in here. And so ln of 17 equals to ln of a, which gives us a equals to 17. Now finally, back to our original function. When t equals to 10, what will be the amount of sales, that is s? So from last part, we put all the A and K's back into the equation. When t equals to 10, S equals to this whole thing, and that gives us 80. And because the answer is in $1 million, so be careful, the amount of sales of the camera after 10 weeks from the start of promotion will be $80 million.